we now have the concept of a quadratic form, which is associated to the concept of the Hermitian matrix representing our quadratic form. And we just saw two techniques for classifying that quadratic form, or that Hermitian matrix, according to its definiteness. Well, why is all of this useful to us? Well, remember that one of the heroes of the course is the Grameen of any matrix. So if we start with any matrix A, that matrix might not be Hermitian. In fact, it might not even be square. However, when we look at its Grameen, which is often the most important ingredient in a problem we're trying to solve involving that matrix, we always get a Hermitian matrix. So the Grameen of any matrix must have a certain definiteness because it is a Hermitian matrix. So the question is, what is the definiteness of the Grameen of a matrix A? Well, it turns out that every Grameen is positive semi-definite. And in fact, there is a stronger theorem which says that the concept of positive semi-definiteness is the same or equivalent to the concept of being a Grameen. So rigorously, we can state this as a theorem. A matrix S is positive semi-definite if and only if S is a Grameen, meaning that S can be set equal to the Grameen of some matrix A. I want to walk you through the proof of this theorem, but the reason I want to walk through the proof is mainly because this proof only uses concepts that we've already used in the course, and the theorem itself is important. I certainly don't expect people to memorize this. So this is an if and only if proof, which means there are two things to establish. The first thing we want to do is we want to assume that the matrix S is positive semi-definite, and then we want to conclude that this implies that S must be possible to represent as a Grameen of a matrix A. So if we assume that S is positive semi-definite, one thing we can do is we can look at its spectral factorization, Q times D times Q conjugate transpose, and remember that D here is a diagonal matrix where the diagonal is home to all of the eigenvalues of S. And if S is positive semi-definite, we then know that all of the diagonal entries of D have to be non-negative numbers. So what we can do is we can take what's called a square root of this diagonal matrix. To take a square root of a diagonal matrix, all we do is take square roots of all of the diagonal entries. So by definition, the square root of D is the diagonal matrix whose diagonal entries are all of the square roots of the original diagonal of that matrix. It turns out that by defining a new matrix A by the formula root D times Q star, we then establish S equals, well, Q times D times Q star, but D is the same thing as root D times root D, and Q times root D is the same thing as quantity root D times Q star, quantity starred. And root D times Q star is the same thing as A star. So this is the same thing as A star times A, or the Grameen of A. So that establishes the first part of the theorem. If your matrix is positive semi-definite, you can represent that matrix as the Grameen of another matrix A by finding a spectral factorization and then defining A as root D times Q star. For the second part of this theorem, let's assume that our matrix S is the Grameen of a matrix A, and let's attempt to conclude that this must be a positive semi-definite matrix. Well, if we look at the quadratic form little q corresponding to S, this is the same thing as the inner product of the variable vector x with S multiplied by the variable vector x. Well, if we substitute in S equals A star times A, we're then looking at the formula x inner product with A star times A times the variable vector x. And remember, if we have matrices inside of an inner product, the matrix can bounce around from side to side, but every time we move a matrix from one side to another, we have to conjugate transpose. So let's now move this A star to the other side of the inner product, and we get A times the variable vector x, inner product with A times the variable vector x. And staring at this for a moment yields a revelation. This is the vector A times x, inner product with itself, which is the same thing as the magnitude of that vector squared. So if our quadratic form is represented by a matrix S that happens to be the Gramian of a matrix A, then we automatically have a nice formula for that quadratic form. We take A, multiply by the variable vector x, that's a new vector, and then we take the length of that vector squared. Well, one thing we know about the length of a vector is that it's never a negative number. And since this formula for the quadratic form has to be a number that is non-negative, we immediately know that this matrix must be positive semi-definite. Okay, so we have a very nice theorem here, but there are definitely some moving parts in the proof. The big picture says that the concept of being positive semi-definite is the same concept of being a Gramian. In the first part here, what we said is that if we have a spectral factorization, we can construct our matrix S as the Gramian of a particular matrix A. And on the other hand, if we know that we're studying the Gramian of a matrix A, then we know that the quadratic form we're studying is the magnitude of A times x squared, which is guaranteed to be a non-negative number. So let's look at an example. Here, we started with a matrix A, and that matrix was 2 by 3. So maybe we encountered this matrix while studying a least squares problem. Maybe we encountered it while studying a projection problem. But no matter where we found it somewhere. And let's say that we decided to study the Gramian of this matrix. Well, the Gramian of this matrix is A star times A. And if we do the arithmetic here, we find that this is a 3 by 3 real symmetric matrix, which we're calling S. Well, what do we know about this matrix S? Well, this matrix is the Gramian of A, and therefore we automatically know that S is positive semi-definite. We also have a nice way of representing the quadratic form corresponding to S. According to our calculation from the previous slide, the quadratic form corresponding to S is the same thing as the magnitude of A times x squared, and A times x is the same thing as taking the inner product of each of the rows of A with the variable vector x. So if we multiply A by the variable vector x, we should end up with two outputs. The first would be -1 times x1 minus 3 times x2 plus 0 times x3. So we're getting that here. Then the second part would be 2 times x1 minus x2 plus 4 times x3. That would be the second coordinate. And the length of that vector squared is the sum of the squares of those terms. And of course, we know that this quantity is non-negative because we are summing squares. Okay, so let's conclude this lecture by discussing another important type of factorization, which is the notion of a Cholesky factorization. So by definition, a Cholesky factorization is an equation that takes the following form. S equals R star times R, where S is a positive definite matrix, and R is an upper triangular matrix with a positive diagonal. So one major theorem in computational linear algebra says that every positive definite matrix has a Cholesky factorization. So it turns out to always be possible to take a positive definite matrix and represent it as the Gramian of a matrix R, where R is upper triangular with a positive diagonal. So let's walk through an algorithm for constructing a Cholesky factorization. So the algorithm is as follows. Let's start with a Hermitian matrix called S. In step 1 of this algorithm, we attempt to factor S as L times U and we ignore the method of partial pivoting. Now, if we at any moment in our algorithm, we require a row swap, we can immediately conclude that our matrix is not positive definite. Also, if at any moment we encounter a pivot in U that is not positive, we can terminate the algorithm and conclude that the matrix is not positive definite. If we get through step 1 successfully, so if we manage to calculate an LU factorization without needing any row swaps, and where U has a positive diagonal, as a positive diagonal, then in step 2, we define a matrix D to be the diagonal matrix whose diagonal entries are the pivots in U. And then we can define in step 3 a matrix R by the formula square root of D. Remember, to take the square root of a diagonal matrix, we construct a new diagonal matrix whose diagonal entries are the square roots of the diagonal of the original matrix. And then we multiply by L star, where L came from the LU factorization. After getting to step 3, we now have a Cholesky factorization. S is guaranteed to equal R star times R, and R will always be an upper triangular matrix with positive diagonal. So let's see this in practice. Here we are starting with a 3x3 real symmetric matrix, which is a Hermitian matrix. And let's do some row reductions. So I'm attempting to find an LU factorization here, and I'm ignoring the method of partial pivoting. So since I'm ignoring the method of partial pivoting, I'm not going to swap row 1 with row 3 to take advantage of the larger 20 here. I'm going to use the number 9 to clear out the entries below it. So I'll have 2 steps in the first step here. I'll take row 2 and I'll subtract 1/3 times row 1. Then I'll take row 3 and subtract 20 over 9 times row 1. That clears out the 2 entries below my 9. Then I'm going to move right 1 and down 1, where I have a 1 as my pivot now. And I'm going to clear out the entry below by taking row 3 and adding 11/3 times row 2. And that gets me to my matrix U. One thing to note is that each of the pivots, 9, 1, and 1/9, are positive numbers here, which indicate that our matrix S is positive definite. And if we look at the steps in these row reductions, we get an LU factorization. Our matrix S is L times U, where U came out of the row reductions, and L is built from looking at the multipliers used in our row reductions, as we've done previously. Now, the Cholesky factorization is calculated as S equals R star times R, where we define R to be the square root of D times L star. L star is the conjugate transpose of L that came out of our LU factorization, and the square root of D is the diagonal matrix whose diagonal entries are the square roots of the pivot positions in U. So the square root of 9 is 3, the square root of 1 is 1, and the square root of 1/9 is 1/3. If we now multiply this diagonal matrix root D times L star, we get our Cholesky factorization, where S is R star times R, where R is this product. Since S is R star times R, we know that S is positive definite, and in fact, we get a nice formula for the quadratic form corresponding to S. We know, since S is the Grameen of R, that the formula for the quadratic form is R times the variable vector magnitude squared, and R times the variable vector has coordinates given by 3x1 plus 1x2 plus 20 over 3 times x3 quantity squared. Then the next term will be 0 times x1 plus 1 times x2 minus 11 over 3 times x3 quantity squared. And the last term will be 0 times x1 plus 0 times x2 plus 1/3 times x3 quantity squared. And of course, this value is guaranteed to be greater than 0 because we're summing 3 squares here. Let's look at another example. Here we're studying a perfectly good 3x3 real symmetric matrix. And let's say all we want to do is figure out whether or not this matrix is positive definite. Well, let's start by doing some row reductions. We're going to ignore the method of partial pivoting and just use this 1 in the upper left-hand corner to clear out the 3 and the 11. When we do those operations, we end up with this new matrix. And if we move right 1 and down 1 to continue the algorithm, we encounter a 0. Now, in this case, I don't have a number to use as a pivot, so I need a row swap. And since I need a row swap, I can terminate the algorithm and conclude immediately that this matrix is not positive definite.